So now we come to our second bonding theory. This is valence bond theory. The Lewis model is an oversimplification. We've been talking about how electrons are particles and waves at the same time, and they occupy these orbitals that are like these weird shaped standing waves, and it seemed all really, really complicated. Then we go to the Lewis model, and all of a sudden the electrons are little dots. You know, we put 2 on the top and 2 on the bottom, 2 on the right and 2 on the left. Obviously an oversimplification. So the more advanced theories use quantum mechanics to explain what chemical bonds are. So we're going to look at 2 of those theories. The first one is valence bond theory. The second one is molecular orbital theory. Both of these are quantitative approaches. They involve predicting shapes and bond lengths and things based on mathematical calculations. We're not going to look at the quantitative aspect of these theories. We're just going to look at the qualitative aspect. It's a lot simpler. So we know that electrons reside in orbitals that are localized on individual atoms. So we had the s orbitals and the p orbitals and the d orbitals and the f orbitals. When we're talking about a single atom, we call those atomic orbitals. When an atom bonds to another atom, those atomic orbitals can change. And so in valence bond theory, we talk about hybridizing the atomic orbitals. So sort of taking 2 or 3 or 4 and averaging them together to make some new orbitals. When 2 atoms approach each other, the electrons and nucleus of the one atom interact with the electrons in the nucleus of the other atom. The electrons of opposite atoms are attracted to the nuclei. The individual nuclei are going to repel each other. So in valence bond theory, we look at the energy changes caused by these interactions, and if the interactions result in a lowering of the energy, then a bond forms. If the energy is not lowered, then a bond doesn't form. So this is a graph illustrating 2 hydrogen atoms as they get closer together. So on the x-axis, we have the distance between the 2 hydrogen atoms. And I'm going to start at this end and talk about the 2 atoms coming closer together. So here the distance between them is quite large. Energy is going up on the y-axis, and we've got 0 right here in the middle. So as these 2 atoms approach each other, there's a little bit of attraction between them. And that's why the energy here is a little bit less than 0. The lower the energy, the more stable it is, the greater the force of attraction between these 2 things. So as we get closer together, they become more attracted. The energy is lowered. And we get to this point, and we get to a minimum in the energy. If we get closer together, as we get closer together, now the repulsion of the 2 nuclei starts to come into effect. And the closer we get, the more that repulsion becomes important, until when we're getting very close, then the energy is going actually very positive, and it's a repulsion and not an attraction at all. Yes?
So what you said from the last slide was that as the energy lowers, so as we hit the minimum, that's when the bond
Right.
is happening.
Yep. So this minimum, the distance between the nuclei here at this minimum corresponds to the bond length. And this energy corresponds to the bond energy. When this bond forms, this amount of energy is released. This energy is a negative energy. It's negative because we just defined 0 at a point, right? And so we're looking at changes in energy, not in absolutes. So you could think of this as being like sea level. And, normally we're doing stuff up here above sea level, right? We know that rocks roll down hills. Well, what if you're up on the shore and you've got a boulder? Will the boulder roll downhill under the water? Yeah, gravity still works, even underwater, right? So here we're going to larger and larger negative energies, but negative energy is lower than positive energy. you can, make these into two people. Here's these two people, and they see each other, and they're kind of interested. And as they get closer and are able to talk with each other, then, they become friends, and they're, just attracted to each other. But then if they get too close, that gets uncomfortable, right? You ever been with one of those close talkers, and they're just like in your personal space, and it makes you back up, right? So that's kind of what's happening here. When they get too close, that's not good. Any questions? You can do all kinds of math and calculate all of this, but we're not going to do that. So that interaction energy is usually negative, meaning it's stabilizing. When you have atomic orbitals that contain a total of 2 electrons that can spin pair. One of the things I always found disturbing about all of this was, well, how are these electrons being okay with being in the same orbital? They're both negative, aren't they? Why aren't they repelling each other? Well, the spin pairing, one spinning up, one spinning down, then they're fine being together. It's kind of a lame explanation, but it's all I've got right now. So we've got 2 orbitals, and we need 2 electrons. Usually the electrons are going to come in 2 half-filled orbitals. Each atom is going to stick out 1 half-filled orbital. Those 2 orbitals are going to overlap, and in that overlap we've got the 2 electrons that spin pair, and that causes more stability, causes the energy to decrease. It's possible for the 2 electrons to come from one atom and the other atom to just contribute an empty orbital. That's called a coordinate covalent bond, and we see those occasionally, but not very much in Chem 1A. So we've got 2 atoms with half-filled orbitals, and they're approaching each other. The orbitals overlap, and then the electrons align with opposite spins, and that's the valence bond theory. Orbital overlap. A summary slide. So we've got valence electrons for the atoms. All the atoms in a molecule are in quantum mechanical orbitals. The bond results when we have 2 half-filled orbitals that overlap with spin pairing of the electrons. The geometry of the overlapping orbitals is what determines the shape of the molecule. So let's look at H2S. So here we have an orbital diagram for sulfur. We're just showing valence electrons because those are the ones that participate in this. Here's a hydrogen, there's its orbital diagram, and here's another hydrogen. So this sulfur has 2 half-filled orbitals, and so we could see, well, what happens when we take this orbital and overlap it with this half-filled orbital from hydrogen? Those should be more stable and form a bond. And then this other orbital can overlap with another hydrogen. So what we're showing over here, the blue circles are s orbitals. They're spherical, and the red balloon-like things are p orbitals. Remember, a p orbital, this is one p orbital above and below. And this is another p orbital, and this is the third one. There are 3 they're perpendicular to each other. So this one is filled. That's this lone pair here. This pair of electrons is in the s orbital, tucked away in the middle there. And then we have these 2 p orbitals that each have 1 electron. And so this one can overlap with a hydrogen, and this other one can overlap with a different hydrogen. The electrons spin pair, and we get bonds being formed. Does that make sense? So the geometry of this molecule would depend on the orientation of the orbitals that are overlapping. Well, s orbitals don't really have an orientation, but these p orbitals do. So this p orbital and this other p orbital, the 2 that are involved in the bond, we would expect them to be at right angles, 90 degrees, right? So valence bond theory predicts that the angle is 90 degrees. VSEPR theory predicts that the angle is something less than 109.5 because this sulfur has 2 lone pairs on the central atom. So there's a total of 4 groups. 4 groups would make a tetrahedron, and we would expect that these would be less than the ideal distance of 109.5 degrees because the lone pairs are more repulsive. The actual bond angle can be measured, and it's 92 degrees. So things look pretty okay here. Any questions? So here we're just looking at atomic orbitals overlapping.